Yeah, none of you guys reminded me also. Okay. So, any answers, guys? What should be the delta omega look like? I mean, should it be high or should it be low? Nayan?
It's small.
Yes, the low, correct. Because the delta omega should be low because and okay, for folks who are going to look at the recording of the material, the recording I started half an hour late. I had forgotten. So what I will do is, after the class is over, in the same in the same video, I will cover the first few slides that I talked, and then you can catch up. So sorry for that. So so delta omega should be lower. So that's the question for a because we want the oscillator to oscillate in a certain frequency, and we want all the frequency components to be in one narrow band, because we want the oscillator to be oscillating only at a fixed frequency. So delta omega should be as low as possible. So when I think Ayush or somebody was saying that the curve needs to be sharp, that's what he was meaning, that this delta omega, if it is 0, then the complete energy content or the power content in the signal will be in one frequency band, right? Okay, so another measure of Q can be given as, if we see here, the lower the delta omega, higher will be the Q. So for a crystal oscillator, Q is in the range of so Q, if you see, is just a number. It's a dimensionless number. So Q can be of the order of 10,000 or 20,000, in that order. This is a very big number, right? So for a crystal, for a good crystal, the Q should be as high as possible, because that's the that is what is going to give you a clean clock, meaning it is going to oscillate with only one fixed frequency, and the frequency is not going to change much. The energy content in the frequency band outside the desired band will be as little as possible, right? So high Q is another thing, another reason why we end up using quartz, right? And for a LCR circuit, if you have a LCR series circuit, you can do the math and see that the Q is inversely proportional to the resistor. This also again makes sense, right? Because as we discussed just now, that the resistor is responsible for energy dissipation in the circuit, and if the resistor is 0, then there will be no energy dissipation, and the oscillator circuit will keep oscillating, and the energy will manifest itself as potential energy or kinetic energy, or a mix of both, and it is going to keep oscillating. But because of the resistor, the energy will die down and the oscillator will stop oscillating. So there can be other, there are actually other definitions of Q, all coming from the same, maths. I'm not going to get into more definitions of Q, but, for us, and actually, okay, another thing, right? So this is a question actually. So let's say you're designing an amplifier, right? And the amplifier, let's say, is a second order system, right? And, that second order system, what do we write as the second order system? S square plus 2 zeta omega ns plus omega n square, something like that we write, and there is a DC gain, right? So can you kind of relate? So let's say this eta that we write here, right? So for an amplifier system, when we talk of this damping coefficient eta, can you relate that there is a relation between this quality factor and eta, right? So you will see in yes, correct, Girina. There is a relation between the quality factor and eta, because for an amplifier, we don't want this kind of an oscillatory behavior, right? For an amplifier, what do we want? If we give a step input, we want it to kind of critically stable. Settle. This is not a critical settling in any case. the critical settling will be like this, right? For a certain value of eta, which we know what is the value, it will critically settle to the steady state value. We don't want the amplifier output to kind of oscillate and settle, right? So for an amplifier, we don't want the Q to be high. So actually, when if you are designing amplifiers, if you want to become circuit designers, analog electronics people, so this is another quick way. So we do Bode plots and we look at the stability of the system. But a quick way to actually get an understanding of how stable is the system is actually look at the time domain response, look at the step response of the system, and look at how many peaks are there. So this is important, guys. This is very important. Not many people will tell you this. So when you are giving, I repeat, so we have an amplifier. If we give a input step, right? And let's say the amplifier output is doing like this and settling, right? By counting the number of peaks that are there, you can actually get a measure of the phase margin of the system. So you need not always run an AC analysis to get a measure of the. So when I design an amplifier, right, I of course the first thing that we'll talk later, actually, the first thing I do actually is to ensure that all the DC biasing of the transistors and everything is fine. And even before I run a stability analysis, right, I will probably just give an input step and see how the time domain is looking like. And that gives me a quick feeling that where my stability is. And so basically when I'm looking at a phase margin, I don't have to go to another test bench or a test setup to actually do the AC analysis. I mean, I of course do the AC analysis finally, because when you are designing the circuit, you have to look at a lot of variations and all that, blah, blah, blah. But to start with, even the transient response gives a good understanding of how stable the system is. So if you have more peaks, the system is less stable, right? So lesser Q. So typically, the number of peaks, we say that if the number of peaks are, let's say 4 or 5, then we say the Q factor is 5. And from that, we can actually, so there are probably white sheet materials you will get, application notes you can get how the number of peaks or this Q factor relates to the stability of a system. So if some of you want, if you're interested, please read that up. But this is very important that, for an oscillator, we want the Q factor to be as high as possible. But for an amplifier, that is just the reverse and that we want, right? Any questions up to this point? Also, can some of you tell me what will happen? So there is one more thing that I'm not mentioned as an important criteria is the power consumption of the oscillator, right? So can you also understand that if the quality factor is bad, right, that circuit will end up consuming more power, right? And that is understandable because this 1 by R, you're losing power, you're losing the energy in the resistance of the crystal. So somebody has to give that supply back that energy, right? So that has to come from the battery. That has to come from the the circuit that you have designed. So that is also another way of understanding that, okay, you'll be consuming more power if your quality factor is poor. Is that clear? That I have not written, but is that clear? Right? Okay. So so these are two different crystal oscillator configurations. So this is what we can use the circuits to make oscillators. So the first one we have connected. I'm sorry, this animation is not. I mean, I didn't want to show the second animation right now. But let's focus on this portion of the circuit, the left guy. So this, if you see, we have a crystal oscillator, and we are actually here. The output will actually resonate based on the series resonant frequency. And the series resonant frequency is dependent on what? The mechanical LM and CM of whatever we drew earlier, right? I mean, if you go back to the series plot, right? Yeah. So this is the series resonant frequency, right? So in that configuration, in the configuration that I'm showing here, the first one here, this is going to resonate in the series resonant frequency. Any guesses why? Intuitively, why do you think it is going to resonate there and not in the second frequency? Just take a shot. Anyone? Anyone, guys? See where the crystal is connected. So the crystal, if you see the crystal is connected in a place where it is coming in the feedback path, right? So what happens as we increase the frequency? If we looked at the impedance plot, right? How did it look like? It looked like this, right? So as we increase the frequency from, let's say this is F and this was that impedance Z, right, of the crystal, right? What happens is as we increase the frequency, this crystal, the impedance starts falling, right, as we increase the frequency, which means the feedback factor from this node to this node with frequencies increasing. So what will happen, right? This portion is giving us the gain, right? So that A beta term, so the Bartesian criteria that we wrote, right? That A beta has to be, the magnitude has to be equal to 1 or greater than 1, right? That condition will actually happen at a lower frequency, which is here, because the feedback factor is going to increase, the beta is going to increase as the frequency is increasing. So hence this kind of a circuit will get locked. When it is oscillating, it is going to get locked at the lower frequency. Any questions on this? Is it intuitively understandable that we have put the crystal in the feedback path, right? And that is not the thing. If you look at the other circuit here, this guy, if you see here, right, the crystal. So this kind of a circuit, have you guys looked at this kind of if I replace the crystal with an inductor, can someone tell me how it is? I mean, what kind of an oscillator it is? If I replace the circuit with an inductor, what kind of a oscillator it is? You would have seen this, right? Maybe you don't remember. So it's a Colpitt's oscillator. Have you studied Colpitt's oscillator in some other courses?
No, sir.
Oh, okay. Colpitt oscillator you have not. Okay. But here, so between these two, if you see, right, between these two circuits, the key fundamental difference is this crystal sits on the feedback path, whereas this guy here on the right, it is working just as a load. It does not come in the fundamental, I mean, it does not come in the feedback path. So the right-hand side of the circuit is going to oscillate in the parallel resonance frequency, right? Because in that graph that I drew, right, the whole oscillation, frequency will lock in the parallel. And when do you think you would like? So you can ask. I mean, does it strike your mind when you want to use configuration on the left versus when you want to use the configuration on the right? When do you think we should use the one on the left versus the one on the right? And intuitively, we understand that on the one on the left will be a series resonance, and on the one on the right is a parallel resonance, right? So when do you think we should use the left guy or the right guy? Meaning under what requirements? So the requirement actually comes from the resonance frequency. If we want a higher frequency oscillator, then we will go with parallel resonance, right? Because that F, whatever we saw that, right, that F E or the parallel resonant this thing that is higher than the series resonance, right? Much higher. So when we require a higher kind of frequency, we will go with the one on the right. Any questions? I'm not actually going into making a small signal model and all that, because then this course will become an analog electronics course. But it is important for us to understand where piezoelectric crystals are used and in which configurations and why. As long as that is clear, the objective of this course will be met. Any questions on this point, guys?
Hello, sir. Sir, I did not get intuitively how you explained this. Like, this was to be used in series and that was to be used in parallel.
Okay. So if you look at that graph, right? And who asked this question, by the way? Ayush, is it?
No, sir.
Okay,
Shubham.
Shubham, okay. So if you look at that impedance plot that we plotted, right, it looked like this. That was clear, right? That this intuitive portion was clear, right? The lower frequency, yeah. So if you see, right, here this crystal is connected in the feedback, right? The feedback path you can understand, right? Because you can see this output voltage V, a portion of that is fed back. So this is in the feedback path that we can understand, right?
Yes, sir.
So if you look at the Barkhuizen's criteria, what did we say? That the loop gain A beta, that magnitude has to be equal to or greater than 1, right? So that means, see, A, the gain, that is constant. In this case, what is the gain of this? That will depend on this guy, this resistor RE, the DC gain, and the resistance RC, right? So A is kind of constant. So what are we left with then? Beta, right? So beta in this case is going to increase, meaning when is the feedback factor more? When beta is more, right? So if you see here, this crystal, as we increase the frequency from low frequency, as we go higher, right? This crystal, because this portion of the curve is what? It is capacitive in nature, right? Right? So basically, as we increase the frequency, the impedance is falling. So if the impedance, so if you can think of this crystal as a variable resistor, let's say, right? As we increase the frequency, this value of the resistance is reducing, right? So that means the coupling from the output to the input, right, in this circuit is increasing. So the beta is increasing, right? So that is correct, right? That is understood, Shubham?
Yes, sir.
Not very confident from what you are sounding.
So I will go through it once again and then ask you again.
Okay.
Like,
Okay. So it's like this. So let's say we have a resistor here, right? So if we keep increasing the resistor value, what will happen? The feedback at some time, I mean, at some point, the feedback will fall to 0, right? If the resistor is infinite, this is becoming an open circuit, right? So then we will say there is no feedback. And if there is no feedback, then this will not work as an oscillator in any case, right? So basically, so that means the beta, the feedback factor, is reducing as we keep increasing the resistor. But in this case, as we are increasing the frequency, the impedance, the resistor's value, the effective, let's say, resistor value, is actually not a resistor. Just to make things simple, I'm explaining it like that. The resistor value is reducing. So beta is increasing. So basically what happens, so it's already 12:58, maybe one more minute and I'll pick it up from here tomorrow. So what will happen is when you actually start an oscillator, right? The A beta component, A is fixed. The A beta component is going to hit the maximum value at lower frequencies. That is understood, right? It is going to hit, the A beta value is going to hit the maximum value at a lower frequency. That is understood, right?
sir, actually I'm mixed up, so I need to look at it again and.
Okay, you look at it and maybe we'll stop for today now. And then tomorrow I'll take another shot at it to explain to you guys. And in the meantime, you can have a look at it. right?
So one more query, like the circuit in the left hand side has a current feedback, no, not voltage feedback.
Yeah, but that is how you look at it actually. I mean, current or voltage, right? That is why do you say there is no voltage feedback on the left hand side? Because finally it's a capacitor is there, right? So if this node goes up, the voltage goes up, this voltage will also go up. I mean, you are thinking of it as a current because you are seeing this BJT here, right?
Yes, sir.
But I can replace that BJT with an NMOS. There will be no problem. We'll discuss this again tomorrow, Shubham, right? You
Okay.
guys can drop out, and I will need to continue with the recording so that the people who are going to see the video, they don't miss out on the first this thing. So you guys can drop out. Okay, so what I will do for people who have missed out on the first portion is I will go back to where I started with. And sorry for the mess in recording. I forgot to start the recording. So quickly in the previous slides, in the previous classes, the last class, we kind of stopped at deriving uh, the electrical equivalent network, right? And we said that to make a proper equivalent model, we need both the mechanical as well as the electrical characteristics to be captured. And so the mechanical portion um, um, is the electrical equivalent for the mechanical thing is let's say given by Zm, and the electrical impedance is Ze. So let's look at Zm first. And Zm, if you see, can be given by what? The voltage across this terminal and the current I flowing here. If I can find out voltage divided by Im, then I can know what is Zm. So what I do to find out Zm, I kind of do some mathematical jugglery. So Vs by Im s, the Laplace domain for this V by I. So that I can rewrite as Vs by Fs multiplied by x dot s by Is and Fs by x dot s. And independently, I can find the value of each one of these guys, right? Independently, right? And going back to that spring and the damper model, in the previous classes that I've discussed, Fs by x dot s can be written like this, that you can derive. I'm not again deriving it because I've already done that, right? And similarly, based on these two fundamental equations, we have an expression for x dot s by Is, and we also have an expression for Vs by Fs, right? So these three uh, components, if we fit into this equation, we kind of land up with ZMS, and this kind of a form looks very familiar, right, to us. And we can proceed to represent this in terms of an inductor, resistor, or a capacitor, right, and a capacitor, right? So if this is the mechanical equivalent, if this is the mechanical equivalent of the resistor and uh, you know this inductor and the capacitor C, sorry, um, then we can, going by what we wrote in the previous slide, we can equate, or we can find an equivalent of the inductor, resistor, and the capacitor. And the inductor will be given by the mass M of the crystal divided by D and K. D we know is the piezoelectric constant. K also we know is proportional to the area, inversely proportional to the thickness. We have derived the value of K in the previous slide, long back in probably class maybe 3 or 4. You can refer to that lecture. And R and C is given by this, right? So, this kind of, if you look at the overall impedance offered by the crystal, we can kind of model the overall impedance. So this is the mechanical arm, and CE, this is the electrical arm. So CE effectively will come because of, if you look at the crystal that I had drawn earlier, right, that yellow colored cube, we had two parallel plates, right? and those plates, because it's across, the piezoelectric material also works as a dielectric. It also has a dielectric behavior. Because of these two parallel plates, we get an effective electrical equivalence, right, of capacitor, right? So this CE comes from the basic structure of the transducer, right? So if that is the thing, we can see that, the crystal is like almost like an ideal tank. Only problem is that we have Rm coming into picture. So this creates some non-ideality, and we have to deal with it. So, but otherwise, between LM, CM, and CE, it behaves as an ideal tank, right? So to make this, make use of this overall impedance offered by the crystal, we can, connect this in some form of the circuit. I mean, we can use some amplifier, and we'll see why we need that amplifier. But this LC tank can be, used to make an oscillator. And so this is what we have, the overall impedance, and this is the, this is how the impedance is going to vary. The initial portion is going to be, I shouldn't say again initial, the low frequency behavior will be capacitive in nature. And this again we can intuitively find out, because these capacitors at low frequency will be effectively, offer very high impedance. So the capacitor value, the impedance value is very high at low frequencies. And as you increase the frequency, the capacitor value kind of falls, right? And so this guy falls, and the overall impedance falls, and we kind of land up at a minima here. And then again, this portion is inductive, because as we increase the frequency, the impedance offered by LM increases, and here again it starts falling, dominated by CE, right? So intuitively you can understand why this behavior will look like that. And then FM and FE, if we do the math, we can see, so FM, which in other words is nothing but the series resonant frequency, is dependent on LM and CM, right? Pardon the suffix here, it's a PPT issue. And the second resonant frequency, which is also known as the parallel resonant frequency, occurs at a much higher frequency, given by the C equivalent is given by CM CM in parallel to CE, right? So this is the impedance behavior. So as I mentioned that, the lower frequency resonance, we call it as series resonance, and the higher frequency resonance, we call it the parallel resonance, right? And then we come to this Bark-Wilson's criteria. Before we go into actually designing an oscillator, it's important to visit the Bark-Wilson's criteria, which says that, if we have a loop, so the transfer function of this loop is nothing but a divided by 1 plus a beta. So this is a typical negative feedback system. But for the system to oscillate, we need this denominator to be equal to 0, because only then it will start oscillating. And that means effectively the overall loop should have a, effectively overall there should be a positive feedback. And that, can be simplistically written as two conditions: that the loop gain should be equal to 1 or greater than 1, and the phase shift around the loop should be multiple of 360 degree. So 2 pi n can be 0. Mathematically n can be 0, but typically, in realistic conditions, n0 is not valid, because it is passing, the signal is passing through elements, electrical elements, and there will be a phase shift. So effectively it will be a 360 degree kind of a feedback or more. I mean, multiple of that, right? So that's what the Bark-Wilson's criteria say. And I think that's where I mean, the video recording I started, I lost some portion of the recording. But for the oscillator to behave, to have good characteristics, these are the characteristics it should have. The temperature, it should be independent of temperature. It should be independent of the power supply and component values, and also it should have a high Q factor, right? And so this is if we put the crystal in feedback, going to the making it look like a Barkhuizen's kind of model, we can say that look, in the forward path where the amplifier A provides a 180-degree phase shift and the crystal provides another 180-degree phase shift. So effectively the loop works as a positive feedback and the loop will start oscillating, right? So this is how the quartz crystal is going to look like. And if we have an oscillator, if an LC tank, right, we will see that if we give a input impulse, it will oscillate, but then the oscillator will die down with time. And that happens if it's an ideal LC tank, this will never die down. It will keep oscillating. But in real world, it will die because there are components which will dissipate the oscillatory energy, right? And that is one important criteria for an oscillator. For an ideal oscillator, we don't want the energy to be dissipated in any form. We want the energy to remain in the system, either in the capacitor or in the inductor, right? The capacitor energy can be equated to potential energy and the inductor energy can be equated to kinetic energy. So in an ideal pendulum, wherein we have, let's say we can think of this pendulum, right, swinging from one end to the other end, right? We know how the energy converts as it swings from one end to the other end, right? So at the extremes, the energy is potential energy. And right at the center, the potential energy is zero and the complete energy is in the form of kinetic energy, right? Similarly, in an LC tank, you will see that the energy content in the inductor at one point will be zero and the complete energy will be stored in the capacitor. And at other extreme, the energy content will be in the inductor and the energy stored in the capacitor will be zero and it will keep oscillating, right? However, because of resistance, parasitic resistance or inherent resistance that comes in the real world, the oscillator will actually tend to die down, right? And because of that, we don't want that to happen, and that is the reason we want a high Q. And also, we can think of Q also from a spectral purity point of view. If we take a clock frequency and if we put it in a spectrum analyzer and plot the power content of the clock as a function of the frequency, ideally we would like the complete power to be concentrated in a very narrow band of the frequency. We don't want the power to be spread because then it's not going to be a clean clock in the sense that it will have more than the intended frequency components, right? So you want delta omega to be as narrow as possible so that this curve becomes as sharp as possible. And that brings us to another way of looking or defining Q factor, which is inversely proportional to the delta omega, right? And also intuitively, we as we understand that the dissipation has to be as low as possible. Q should also be inversely proportional to the resistance. If we think of that LC tank circuit as a series kind of a circuit, and so the Q is inversely proportional to the resistance in the circuit. So I think that's where we started the recording of the class, and hopefully I kind of went through the initial few files pretty quickly. But in case any of you have any questions or doubts, please send me an email and I will be happy to get back to you. So thank you guys. Yeah, have a nice day.